In this video, we're going to explore the concept of stoichiometry. So in the last few videos, we've looked at how the mole can be applied to chemical formulas. In this video, we're going to look at how the mole can be applied to a chemical reaction. So to refresh your memory, a chemical reaction is where you have a set of reactants that come together and then they make a set of products. What we're going to be interested in stoichiometry is the ratios between these reactants and products, meaning how many of each reactant do we need to go into this chemical reaction in order to produce however many products we're going to make. So to kind of get started in a place where we are all familiar, I use the example of making a sandwich because this gives us a starting point where we can look at all the main concepts in stoichiometry with a very simple example without having to do any heavy lifting with unit conversions or anything like that. So let's just start by thinking about this. So if we have 2 slices of bread, 1 slice of meat, and 1 slice of cheese, we can make a sandwich. So this is basically a recipe. Now, we have a pretty good conceptual grasp of this. So we could ask some pretty simple questions. If you have 2 slices of meat, how many slices of bread would you need? How many slices of cheese would you need? How many sandwiches could you make? These are all things that we can do relatively simply just in our mind. So if we have 2 slices of meat, we know that the ratio between meat and cheese is 1 to 1. So if we have 2 slices of meat, we would need 2 slices of cheese. We know that for bread, the ratio is 1 to 2. So for every slice of meat, we would need 2 slices of bread. So that would mean that if we have 2 slices of meat, we're going to need 4 slices of bread. How many sandwiches could we make? Well, if we have 2 slices of meat, and for every piece of meat we can make a sandwich, we could make 2 sandwiches. Let's look at how we can actually do this in a more systematic fashion. So is there a way that we can construct some unit conversions that allow us to do this without necessarily having to just do it in our heads? And there is. So if we have 2 slices of meat, we can use the ratios. So in the case of doing the meat to cheese ratio, we see that we have a 1-to-1 ratio. We can say that for every 1 meat, this is going to equal 1 cheese. And now we have a unit conversion. So for every 2 meat, we can say, well, for every 1 meat, I need 1 cheese. And my meats are going to cross out. My units of meats are going to cross out. So now that's going to give me 2 cheese. Now let's do one where we have not a 1-to-1 ratio. So for every 1 meat, that's going to equal 2 breads. So we have another unit conversion. So we can then say for every 2 meat, we can then put 1 meat on the bottom, and we can put 2 bread on top. So this is going to give us 4 slices of bread. So we're developing a system where we can use unit conversions to help ourselves out. And at this point, I'm going to show you something that's going to be very useful to you. In essence, when we're constructing these unit conversions, any of the coefficients in the reaction can be used to create a unique unit conversion between any one of the reactants or any one of the products. So now let's look at a different question. So if you needed to make 10 sandwiches, how much of each reactant would you need to buy from the store? So this is another way of looking at it, right? We can go in the other direction. We can say, well, I need to have a certain amount of product. How much of the reactants would I need? So in this case, if I needed to make 10 sandwiches, let's say that I wanted to figure out how much bread I would need. Well, we can create a unit conversion for this where we say for every 1 sandwich, that needs 2 bread. So we can say, okay, so for every 1 sandwich, we need 2 bread. So that would give us a total of 20 bread slices. And you could do that for all of them. I'm not going to go through it and do it for all of them, but you're starting to see what I'm getting at. These unit conversions that we can create are going to become what we call the mole ratio between the two. Okay, so now this is a really good question. If you have a loaf of 12 slices of bread, a package of cheese that's 10 slices, and a package of meat that's 8 slices, how many sandwiches can you make? What reactant limits the amount of sandwiches you can make, and how much of the other items would be left over? So this is what we call in chemistry a limiting reagent problem. What that simply means is, when you have a limiting reagent problem, is you have a recipe. You have some stuff in your pantry at home. You may not necessarily have all the stuff that you need in your pantry. So one of these different things may limit how much you can actually make of this recipe. So now let's try this out. So we have 12 slices of bread, 10 slices of cheese, and 8 slices of meat. So what we can do is we can check, well, how many sandwiches can I make from each one of those various components? So if we have 12 bread, 10 cheese, and 8 meat, we can test this out and see how many sandwiches we can make from each one of these. So for the bread, I know that I need 2 bread for every 1 sandwich. So the most I can get here is 12 divided by 2. That's going to be 6 sandwiches. For the cheese, I know for every 1 cheese, I can make 1 sandwich. So in this case, I could make 10 sandwiches. And then for the meat, it's the same. I need 1 meat for every 1 sandwich. So this is going to equal a total of 8 sandwiches. Okay, so which one of those reagents is going to limit us? Well, it's going to be the bread. So we call this the limiting reagent, or the limiting ingredient, meaning, yes, I could make 10 sandwiches from the cheese and 8 sandwiches from the meat, but what's going to happen is before I make those sandwiches, I'm going to run out because I'll run out of the bread. So that's what we call the limiting reagent. We call these guys the excess reagents, because these are going to be left over, and the limiting reagent is used up. So we just did before we even talked about chemistry, we just did a limiting reagent problem, and I showed you the whole process. So this is what I'm trying to do in this video, is to basically just give you an overview. Now let's look at the second part of that question. So the second part of that question says, well, how much stuff is going to be left over? Well, if I know that my limiting reagent is equal to the bread, let's see how much of each of the other components I'm going to use up. So if I have, let's check and see how many slices of bread we had. We had 12 slices of bread. So if we had 12 bread, we can figure out how much cheese that's going to use up. So for every 2 slices of bread, we use 1 slice of cheese. And the same thing for meat. For every 2 slices of bread, we use 1 slice of meat. So in this case, we're going to get 6 cheese that we use up and 6 meats that we use up. So how much is going to be left over? So what are you going to have for leftovers? Well, if I had 10 cheese minus 6 cheese, that's going to give me 4 cheese left over. And if I had 8 meats minus 6 meats, that's going to give me 2 meat left over. So this is what we call the excess from the reaction. So that's going to be stuff that's left over that's not going to get used up in the reaction. Okay, so that looks at that particular part of the problem. Now, this is the next part of this question is where we start to make the transition into chemistry. So it says, what if you had 1 mole of meat? How many moles of the other reactants would you need? How many moles of the other sandwiches could you make? So what this is getting at is, because these numbers in these coefficients, these apply to a number of things. So if we had 1 mole of meat, that would mean that we had 6.02 times 10 to the 23rd meats. Now, let's think about how much of that let's think about how much we would need if we needed in terms of cheese. So if we had 1 mole of meat, that would be a lot of meat. How many cheeses would we need in order to, in terms of moles, would we need in order to do this? Well, we can set this up as a unit conversion. So if we had 1 mole of meat, that's going to equal 6.02 times 10 to the 23rd meat. So using our ratio, for every 1 meat, we have 1 cheese. that's going to equal 6.02 times 10 to the 23rd cheese. So in essence, if we had 1 mole of meat, we would need 1 mole of cheese. We could make 1 sandwich. We can make 1 mole of sandwich. And we would need 2 moles of bread. So in essence, the key concept here is we can either think of those coefficients as a single atom coming together in the reaction to make a single atom or molecule of product, or we could think of this as moles of these reactants, because remember, a mole is just a number of things, and the ratios don't care about what the overall number is. So we can either think of this as 1 molecule of meat and 1 molecule of cheese coming together, or we can think of this as 1 mole of meat and 1 mole of cheese coming together. So now the last thing I want to do is I want to construct this in terms of more of a chemical sense in this first introductory video. So let's take a reaction like N2 plus 3H2 gives 2NH3. So this is our first actual chemical reaction. So what I'm getting at is, in this reaction we would need 1 molecule of N2, 3 molecules of H2, and 2 molecules of NH3 would be the product. Now we can extend this to moles, because we know that to go from molecules to moles, there's a constant multiplier of 6.02 times 10 to the 23rd. So I could say, well, if I had 1 mole of N2, I would need 3 moles of H2 and 2 moles of NH3 as a product. So that's kind of the key concept here. We can either think of this in molecules or we can think of this in moles. So now what we're going to do is we're going to extend our unit conversion helper. So in our unit conversion helper, we had that for a given mole, we can convert to mass, and we can use grams per mole, or the molecular weight there, to help us go from mass to moles. And we can also use Avogadro's number to go to the number of whatever it is, number of particles. That could be atoms, molecules, whatever. It could be meats or cheeses or hydrogen molecules or nitrogen molecules, it doesn't matter. And we know how to use these unit conversions. We've been doing this. But now we can extend this where we can go from mole of one thing to mole of another. So we have mole of A, and we can go to mole of B. What I mean by A and B is, let's say that I have information about nitrogen, and I wanted to get information about hydrogen. Well, I can do that by using the mole ratio. And once I get to moles of B, I can then go to either mass or the number of particles, it doesn't matter, using my unit conversion. So this is very powerful in this case, meaning we can take a mass of one thing, convert that to the number of moles using the molecular weight, use the mole ratio of A to B to allow me to get to moles of B, and then once I'm in moles of B, I can get to the mass using the grams per mole of B or Avogadro's number. So let me show you just a couple of quick examples. Okay, so let's say that we had 14 grams of nitrogen, and we wanted to know, with that 14 grams of nitrogen, how many grams of H2 would we need in order to run that reaction? Okay, so if I had 14 grams of nitrogen, we're going to go to moles. So our first step in this case is going to be to go from mass to moles. So we can do that, and we can divide by the molecular weight, which is going to be 28 grams for every 1 mole of N2. So I got my 28 grams by looking at the periodic table. The periodic table mass for nitrogen is 14 grams per mole. So if there's 2 of them, that's going to give us 28 grams per mole. Hence why I chose 14. It's just because it's going to be a round number. Okay, so then now we're going to look at, well, now I know how many moles of nitrogen I have. So we can convert moles of nitrogen to moles of hydrogen by using the mole ratio. So I know that for every 1 mole of nitrogen, I need 3 moles of hydrogen. So for every 1 mole of nitrogen, I need 3 moles of hydrogen. And now the problem is asking us for how much H2, and let's just add in grams so that we don't get confused with moles. So now that I have moles of hydrogen, I can follow my conversion here. So first we went from mass to moles, then we went from moles of A to moles of B, and now we're going to go from moles of B to mass. So from here I can say, well, for every 1 mole of hydrogen there is 2 grams of hydrogen, and I get that from the periodic table. So now if we do this out, if we do 14 times 3 times 2, and then we divide by 28, that's going to give us 3 grams of hydrogen. So you can see that this is a very powerful, this chart right here is a very powerful chart because it summarizes all of the main unit conversions that we have in relation to the mole, and now we can go from the moles of any one reactant or product to the moles of any other reactant or product, and then once we're there, we know how we can get the number of particles or how we can get the mass, because we know the molecular weight and we know Avogadro's number. So this really summarizes the key concepts in stoichiometry, and we're going to start to apply these to some real stoichiometry problems in the next video.